So let me just switch off the video so that bandwidth will be all right. Okay.
Sir,
So
can you make it full, please? Full screen.
uh, I'm
As well.
I'm putting in the full screen mode
Okay.
only. Uh, now is it okay?
Yes, fine. So हाइट
Okay.
पे भी थोड़ी हाइट वाला भी कर दीजिए, नीचे वाला दिख जाएगा अच्छे से.
Uh,
थैंक यू सर.
okay. So today we'll discuss about the planning and design of smart microgrid with switched networks. So this is one of the very important aspect. Generally, we do not discuss more in this one because generally we are busy with one of the component to develop, and that will take lot of times for us. But all this component, how to be implement and how to be designed and how it will be connected is very very important thing. Uh, so just 1 minute. So this microgrid, generally, if you see different kind of uh, there are different kind of geographical structure. There are different kind of geological geographical structure and different kind of weather condition around the globe. And one microgrid design may not be suitable for other place, or other place microgrid design may not be suitable for other place. Somewhere solar is very prominent, somewhere wind is very prominent, somewhere wind solar is prominent, somewhere you cannot do, sometimes the geothermal is the solution. So that is why the design and planning is the most important thing for each geographical locations. And second thing, when we don't design a smart system, then lot of demerit in the conventional power system. So that will also come into picture. So before starting this one, this is already introduced by Neha. So this is our mainly my research activities are power electronics, wind, wireless power, EV design controllers. And there are also one of the most important aspect is our motor development, design, controller design, and complete structure for electric vehicle, for the ship propulsion engine, and many big power electronics components we develop in our lab itself. And also we have a complete setup we have shown. And there are a few technology which we saw in the different form in the Delhi, in the ministry, in many places. When they invite us, we display. There are a lot of smart transformer, inverter, so many things. So this is our team. Now team members have changed many. And this is one of the product which display is a foldable electric vehicle. You can see that a very small electric vehicle we develop, and this is very this is foldable like a suitcase. You can develop this one, and we got around 5 crore rupees for the further development of these EVs. Okay, so and these are the two books which we publish. So, what is the today's electrical power challenge actually? One is aging infrastructure. Second one is reliability. Third one security. Fourth one market dynamic. And then rate and pricing. Now the distributed generation and that the independent power supply from your local support, and efficiency and optimization, and which is required during the peak response or peak control, and rising energy cost day by day it is rising, and the oil price as well as the other security equipments. And conservation is very important thing. That is what the carbon dioxide emission must be reduced. Those are nothing but to conserve the energy. Mass electrification, which required that every village, every town need to be uh, electrified. Uh, then renewable energy integration, and which is very important nowadays, that people thought that the renewable energies are one of the great this, and then green energy. Mhm. So if we see here the uh, growth of the amount of renewable energy. What is the problem with the renewable energy? Is the intermediate nature of the renewable energy, and this you cannot store this energy. You require very large batteries, and also you need some kind of prediction techniques for predicting what will be the expected outcome. Accordingly you can plan, okay, whatever requirement for planning, very essential. And that is what the second is, the transmission loss. So that is why the, if you see a transmission line flow in a long transmission system, and then there is also, but you will see that nearly 26% of the electricity are wasted. And also energy decentralization will make us a very great. That is what distributed energy resources are one of the important platform for doing this one. And also the frequent power outage is one of the another aspect of this one. The frequent output, frequent power outage, and the common cause. You will find that in the village, especially in the Bihar here, we have, there is a frequent power cut in the village areas, because if some leader come in the Patna city and they require more electricity, they switch off the less priority areas like villages. They switch off, and they supply the entire power to for the this type of activities. So that is why the energy, to increase the energy self-sufficiency, the battery and the protection system are very important thing. And that then there is a electromobility, is that the electric vehicle today, and you will see that nowadays these EVs are fastly growing technology, and they are also connecting everywhere. And you will find after some time IoT everywhere, like that EVs will be everywhere, and that will be used. You need a smart grid technology for for controlling this all the thing. And then grid modernization is one of the important, because you know that this grid is operated since time, since long time. So if you go first AC transmission line, which is erected from the Frankfurt to Leuven in Germany, you will find that those electricity, those lines and our today's line, there is a lot of differences. Why? There is a grid modernization. That was the 120-volt to 133 hertz frequency, where today we have to 20-volt and 50 hertz frequency. So there is a lot of modernization is a very important thing. And it is very costly. Special the transmission line design is very costly. I can tell you, when our new IIT came up in the Patliputra colony of Patna town, so in that colony, to get a power from Digha, there is a place around 6 kilometers from IIT, and to get this power in a dense area, you cannot go for underground, you cannot go for the overhead line. So how to design? Because the Patna city is very densely populated. So in which way you want to take the power? And you will see that a new construction of a new transmission line is really, really challenging. And even if old transmission lines are there, and you want to overload those things because the conductor rating, everything is limited. Extra 500 kilowatt of power to flow to IIT is required extra conductors or extra infrastructure altogether. That is why the energy decentralization is one of the beautiful the solution for this type of this. And threat of the terrorist attack, you must be knowing that there are a lot of place. For example, there is a community hall in Patna, and the attackers who, because those who were electrician, they are being removed. So what they do, if they know where is the switches, so they come and operate the switches in the critical hours. So they are nothing but it is like a threat also terrorist. So similarly, the microgrid system, when we have developed a microgrid system for local distribution and generation, that is one of the best solution and best thing. So, so if you see this one, the topology of a smart grid, you have a co-generation power plant and network intelligent wide load profile. So co-generation like wind, solar, this, and you require data control, energy flow, and that is required, and to design a smart microgrid system. And that is what, if you see this one, why microgrid planning is required. You see, for example, here you see one solar plant, another solar plant on the rooftop, one solar plant on the rooftop, but there is a clearance angle. So, what is the challenge here? The challenge here is that in this rooftop, there is a heavy wind, and somehow the wind will blow inside the below solar plant. It will blown out very quickly. It will throw out from this because there is no clearance angle. Where the above the picture, you can see that there is a clearance angle. We designed this solar plant in our old campus, and it is a 10 kilowatt solar plant, and you can see that there is a clearance. And you can see that there is an optimal design that during winter and during summer, there is a nearly 8 degrees the incident angle differences. So you need to find out what is the optimal angle of incident during winter and summer. And that is also studied. And then we have given the wind clearance of 200 kilometer per hour. And this is the exact design which we have or you can see on the above one. But below one is without any planning. They have just simply put the solar panel. For example, wind. So when you have wind, which is the best site? Good site is there where you can see that first one is a good site, second one is bad site, and third one is a obstacle. So these type of things always need a design and planning. When we see the evolution of the smart grid, you see that there is a central generation. Then you have a transmission system. Then we have a substation distribution network. Then connected. So what we do nowadays, we create a microgrid having a local load as well as co-generation storage, and we control that one. Sometime we would feed to the grid, and also sometime we will take from the grid. So this is very, very important thing, that this is that our substation can be reconnected if you have the substation has the capacity to absorb the extra amount of power. according to beyond its rating. And that is what this is evolution, how it started from this one. So one can, if you see here, uh, the smart grid cannot replace the existing electricity grid. If you see nowadays our conventional electric network is there, can we make that same network as a smart grid? No, it's very difficult. And the cost will be nearly two times the cost of a new smart grid development. Because you have to design the component which is exactly matching the existing component of the existing transmission system. For example, you have, for example, fan of uh, 120 volt or 220 volt 50 hertz system is there. You have to design the component for that particular thing. And that is what there is a smart grid and the grid. They can coexist together, but the existing grid cannot replace entirely by the as a smart grid. That is why the research focus nowadays is on the protection, switching, dispatching, control, management, etc. are a very important thing. And then regulatory and standardization of the components, interfaces, and subsystems of a smart microgrid. Then communication, messaging, data networking, and automation of the smart microgrid component and system are the there are a lot of researches going on this way. Then the smart grid, actual microgrid, require network approach. How the network approach? For example, you have a simple electrical network of a RLC circuit. And what is the microgrid? Microgrid is nothing but there is a local generation and then the loading and there is a inverter then you control this one, and that is why the network approach allowed researchers from diverse fields to work together to develop the solution. If you see, for example, I was working with a company in the G Bangalore, and they have to erect around 1 megawatt wind farm. So if you see that one, you will find that in the wind farm, most of the people are from mechanical background, and they are mechanical students. And this mechanical background will give they are all mechanical background or some control or electronics like that. So if you see this one, if you find this network approach, that they can easily understand the electrical network very easily rather than understanding the equivalent circuit of a parametric values. So this I have seen that there are so many people they have come in contact with this one and they could able to develop different kind of solution for the different kind of network approach. When this type of network approach is there, then that will make us more. So what is the design procedure? Is one of the design process and the guidelines are very important thing. And if you see here, there are these benchmark comparison. The design you required, the very important thing is that there is a benchmark in this design. So what is the benchmark problem? That there is an existing network, and that existing network will compile or will design initially, then once you element wise design you do, then it comes second one comes the microgrid, and then how to design, how to control that one. After controlling that one, then it comes as a then modeling information. And modeling requires a lot of information inside and outside also. And that is how the modeling thing will very important thing here. So uh, if we see there are mm,
is coming online. So we have one more person, one observer has joined. Professor
so,
Ranjan Kumar Behra has joined from IIT Patna. So yes, go ahead. Yeah.
so uh, the important in the design procedure is one is the modeling aspect, and then information, and then power and communication modeling is one of also very important things in. And when we see this the modeling and control, then you can see that there is a design criteria. For example, what are the design criteria? Mhm. Just 1 minute. Okay, just one. Somebody came. So if we see here, there are few design criteria, and there are also standards given, like IEEE standard we have, and nowadays Indian wind tunnel standard also coming to picture. So then there are different data required, and also specifications. And after designing this one, there are different controls. For example, the voltage control and frequency control, and also protection, energy management, and load management. Once this is developed, then you can test or validate anything. The components of the design procedure are there are some microgrid benchmarks. You can see that there are a few microgrid benchmarks are available in this, and there are different kind of microgrids. So one is that remote community based microgrid, campus microgrid, and military base. So so this military base, I remember we have developed one of the solar plant in the Air Force Station in Port Blair Air Force Station, and these microgrid are they around 1 megawatt. This PV microgrid and microgrid elements modeling. So there are different. One is generators. Second one is energy sources, what are available. Third one, load modeling and local energy storage option. That is why there is a more trade-off identification modeling also, because every component we cannot model very quickly. So when the design process, if you see, first thing is the control system design, and the design is must be identified and it must be controlled according to our specific requirement. For example, you design an inverter which can feed the our common up point of common coupling with 230 volt 50 hertz for single phase, 440 plus 50 hertz for three phase. And then information and communication technology, that is also today everywhere, the people require the information for data storage as well as also compilation prediction. So many things are required, and communication system is required for the automation and auto turning on turning off switching networks as well. And this combined power and ICT modeling also very important thing, and they are also approved. Then system identification, that is the grid connected system, whether it is islanding system, and that need to be also understand. Then there are few case studies development, and I'll show you some of the case studies which is already existing around us, that this there is a lot of the discussion in this one. And after this, so then it is there are also the energy management of generation, storage and load are very. Then testing validity, there are a lot of real time simulators are available, or hardware in loop simulation, and that can be developed by using this different type of the real time simulation system. So the design objective is, first one is environment friendly is very important thing, and the second one, that reliability of the power supply is very important thing. Third one is renewable energy integration, is a there is the injection of renewable energy with ample amount of ripple into the grid also, that is possible. And cost reduction, because the cost, operational cost of the very high, and economical dispatch also, and increases the efficiency increases when the loss reduces. And then operational flexibility, energy, that is also very important. So if you see, there are three type of microgrid benchmark which we were just discussed. But if you see, it is a very prominent network. Okay, there are three microgrids, and one is typical campus type microgrid, and utility microgrid, and SIGRE microgrid. So campus type microgrid, type of microgrid is that you see point of interconnection here, and then we have this microgrids. You have three phase, 3 into 500 kVA, this microgrid, and then you have microgrid controller is there. Mhm. Then you have islanding contactor where you can isolate the grid from this one, and then you connect. There is a AC/DC and DC/DC pull up this, and this is campus microgrid is one of the microgrid design guidelines, and case study is given. And second one, typical campus type microgrid, there are different type of this. So you can see the communication system, charging station, storage, drive, all these things are connected. So when we see this one, there is also a utility microgrid. What is utility microgrid? This is actually SIGRES microgrid, and it is around 25 kV overhead line. and a zigzag transformer, and this is taken the aerial photograph. If you see the utility microgrid, it is having 400 kVA diesel generator, and this, then 200 kVA induction generator, and then all other all other thing. And you can see that there is a battery also, 100 kilowatt hour, which is connected. You can see this is component wise. You can see there is a switches which is here, and then you have a braking rheostat also, or current controlling inductors also there, or bypassing also. And then we have a transformer, then we have a different type of generator, induction generator, synchronous generator, motor, like that. All these things are connected, interconnected system here. So the Sigra microgrid is very, very important, is that here is that this is a flexible modeling. You can, it can work as a mesh type of, and also it can work as a radial structure microgrid, and medium voltage, including the sub network of three-phase main lines. Okay. So if we see this one, this is a North American power system, which is a benchmark medium voltage network. So each component modeling is one of the important thing, is that synchronous generator modeling, and model of renewable energy sources, transmission line model, load model, and model of communication system. So if you see, this is a simple, mm, simplified generator model, and also there are also some the model of renewable energies also you can have, you can model. And also if you see this one, this type of thing, so first we will take a very simple model of the design for onboard uh, plug-in electric vehicle. So we developed many EVs, and we develop also chargers. So this charger is especially we are testing for giving charge from the solar supply. So we have a solar plant here, and that solar plant is producing this solar power and feeding to this grid. So if you see, there are a lot of electric vehicle chargers, okay, and there are onboard, offboard, and integrated, non-integrated, single stage or dual stage generally. If you see, according to available data or standards, there are onboard chargers and rated power from 1.4 kilowatt to up to 240 kilowatt level 3 charger, which is available in the detail in the different then you have DC AC chargers also, DC chargers also, and there are fast chargers which can be also. So if you see, there are few companies they have like this. So one is that non-integrating charger topology are very, very most commercially used in the onboard chargers, and then uh, d- design level 1 and 2 maximum power up to 22 kilowatt. And because nowadays a lot of charging infrastructure is required for everywhere, and key target is to attain the maximum power level or maximum power transfer capability. That is the main purpose of our all kind of different chargers are being used, and with the maximum power with no pollutant or no ripple in the output voltage or current. So there are dual stage where we have AC DC, again DC DC. This type of are very commonly used thing. But if you see, there are many power factor correction converters are used, and that is to feed or to develop AC/DC charging or AC/DC technologies. Also, there are DC/DC converters, and most important converter in DC/DC converter is because you require isolation is a very important thing, because and that way we have a dual active bridge converters you can see here, and then CLLC resonant DAV converters. This. And there are also few single stage, and then if you see this DAV converters, these are the a single DAV converter with front end converter, which can develop. Also, there are matrix converters that is can charge the battery. And nowadays, the traction integrated charging topology also available, where that is, and also if you see here, there are integrated charger with a permanent magnet machine, and this is with their induction motor. So if you see, the best suitable topology for EV charging is this one. Our that we have here solar panel which is connected to common DC link voltage, and we have the charging inlet connecting to AC DC converter, the PV panel supporting this and a common DC link voltage. Then we have dual active bridge converter connecting to the charger or the battery pack, and it is very simple, and bidirectional power flow is possible, and electrical isolation, high efficiency. Modular structure mostly used by commercial available charger can be integrated with the PV panel. So this is the DAB dual active bridge converter, which is you can see there are two bridge, bridge 1 and bridge 2, and they are H bridge inverters. Okay, and there are also different power flow from one bridge to another bridge, depend on the phase shift angle. For example, you want to flow power from bridge 1 to bridge 2, then this bridge 1 or H1 pulse must be leading to the H2 or H5 pulse. That is how. So they depend on the phase shift angle, and generating the phase shift, the duty ratio of 50%. And this is the power transfer equation, you can say. So if you see, for modeling of this complete dual active bridge converter, we have a discrete, this is our current in and I current based on this, and this is a small signal, large signal or small signal perturbation, the modeling also you can do. And based on small signal model, we got this output voltage is distributed. And output voltage disturbance is affected by the change in phase shift, change in output current, change in input voltage. And that is you can see from this one, this figure, where it is given that disturbance factor affecting the output voltage. If you see this one, this is a conventional control method, but that the voltage generated because we know that the phase shift caused due to disturbance, and this one, this is given, and this is actually control loop we proposed, and this way we have developed the or the output to load current transfer function. You can see here, and also this is robustness against the parameter variation. This if there is a parameter variation, we can try to also develop the. So voltage tracking performance can be observed from here. You can see here from the plot of the closed loop transfer function. And impulse voltage fluctuation also can be here in this one. So we developed initially 1 kilowatt and 200 volt input with 50 volt output. So here we can see here that there is a reference voltage change. You can see that also it is also following that one. So this way, this the DAV converter, and there is sudden change in the load also that is shown. And this is the prototype of dual active bridge converter, which I developed, and this one in the, and then this is these are the waveform of the modulation. Then we have developed a modeling controller for direct drive PMSM method. So you can see here, this is a wind turbine. You have a two converter. One is a generator side converter, another one is grid side converter. So the generator side converter we can model in this way, and you can see here, this is the generator. Uh, Generator based the modeling, and the generator side there is a permanent magnet synchronous generator. Then you have a AC/DC with common DC link, and then we have optimal current vector calculation. Then it will. So this is the modeling, simple modeling of the permanent magnet synchronous generator and grid side converter, the DC link voltage VDC1, VDC2. And this is our current control. This way we control this. And this is the PMSG modeling. And if you see here, although you can see from the waveform, from the current waveform, as the power fluctuate, okay, because it is a wind turbine, wind speed also fluctuate. The current magnitude you can see that changes, but the voltage remains constant. So this is what one of the observation here, and it is a 3 level, and the current also it is connected, and then it is a speed you can see, and this is the speed pattern, and also this is our power generation. So everything which is a very important concept altogether is that the generation, the speed, and it is acting like a maximum power point tracking. So whenever the speed changes, that time your power also changes. But one of the important thing when we use a multi-level converter and it is having loaded, then you can see that there are two capacitors, and one capacitor is charged around 550 volt. Another capacitor is charged around 350 volt. So as this, there is a lot of difference between these two capacitors. There will be unbalance. There is also there is associated with common mode voltage. So we need to balance this one. So a chopper circuit is used for balancing this DC voltage. So if you see this chopper circuit, that you have two inductor that can One can charge, another can discharge. So C1 and C2 can be loaded nicely. So if you see here, this is the DC link voltage. Now you can see that it is a very constant. So DC link voltage is always constant. And both the voltage also VC1, VC2 are balanced. And then grid connection standards for wind farm is first thing is voltage ride through. And this one we have turbine should stay connected and contribute to the grid. Mm. They should connected, and the wind farms should generate like conventional power plant. If you see here, you see the first grid code requirement is that even if there is a 15% of voltage drop, 100 to 15% voltage drop, still the wind farm should be connected. And then you will see from the right hand side that is German and Spanish code. And that is what the main objective is, that even if there is a fault in the system, the wind turbine should never stop. They must produce the power and must feed to the grid. So if you see, this is our network profile voltage. You can see this is the simulation result. And then you can see that phase voltage and phase current. And then there is a voltage sag. You can see here voltage sag. And when there is a voltage sag, you can see that time also descending voltage try to keep constant. This is very important thing. Then if you see here, when there is a voltage sag, you can see that modulation index goes high during that period. And also that time this is the neutral current during the voltage sag. And DC link voltage, you can see it is 800 volt. And DC link voltage across each capacitor, VC1 and VC2, are maintained during the voltage sag period. During the transient period also, the voltage remains constant. And this is the modulation index. When V comes down, then modulation index go to higher, and then it maintains. After that, the low voltage modulation index will produce two level, and high voltage is it the as this two level. It shows as a two level converter, and three level converter shows as a two level converter. And when modulation index is high, it shows the three level. Then you see there is that the modeling control design grid connected CSI, component wise modeling. That is what we are seeing is the component wise modeling. And component wise modeling will give us more insight into the complete system's behavior. So if you see here, this is a PV, and a PV is connected through a large inductor, so that it will behave like a current source inverter. And that feed through this inverter, through the filters and connecting to the grid. So this is the control schematic diagram. Mm. And you can see here, this is the control diagram. And you have a three-phase PLL, then you find out theta, and then you feed that theta to this and this modulation index, modulation to generate the real modulation index, and then you can then this PI controller, and this is a complete close. And this is a mathematical modeling. You can find out any paper, that is not a big deal. But the three generation I told you in the morning, that SA1, SA2, and SA3. So that will give you the this modulation. So you see, this is also this link inductor calculation. This is the plant model. And this is the phase and magnitude model of the kernel. Then constraint for CSI pattern is that in the current source inverter is a really peculiar. One is you have to have only two switch on at a time. If more than two switch open, then there will be uncharacteristics harmonic. So this that is why the switching must be perfect. Here you can see that each component is operating for 120 degree, and 120 degree is operation is doing, because one from upper, one from lower, it will go. And then we have a PWM box scheme, and then this is our DC link tracking, and then injection of UPF. So this is the modulation signal. This is CSA present, and this is the three-phase output, and this is our TH FFT, and this one is output filter, inductor, and capacitor voltage, and then this is our voltage, and this is our PLL. So you can see here PLL, it is tested, and within around one and a half time, it is actually tracking the system. And this is what, this is the hardware setup where you can feed the power back to the grid. You can see here a small video that how this system, this is one of our student, Jitendra. He's in Poland. He developed this one. So this is the current tracking error and very few things. So if you see here, there are various studies we generally do for this microgrid. First one is the energy management. And you can see here voltage control, frequency control, transient stability, protection, and vehicle to grid impact, and power quality. There are so many varieties of requirement. A structure of two generating load model can be the element-wise modeling. Load modeling is one of the best, one of the very important also. It is very difficult also. So then current source-based load model, then grid connected inverter. And this is a grid tie inverter-based modeling. And grid tie inverter have a controllable, used for controllable load, and this is a PCC, and this is our inverter. And there is this controller, we can use it for this, controlling this one. And there are so many varieties of simulation. One is power flow analysis. There are so many varieties of methods. Gaussian, Newton-Raphson, perturbation theory, there are so many. Dynamic simulation is that the differential algebraic equations are solved, and then economic dispatch and optimal power flow is also, and then fault analysis is one of the most important. Load frequency control, operator training simulator, reliability modeling and simulation of power market. So these all the things are major driver for the power system for operation. And today modern microgrids try to accommodate all and partial of this all these thing is going on actually. So there is also grid smart grid communication, and in IIT Patna, especially synchrophaser initiation is done in one of our lab, and this wide area monitoring and control transmission required communications of large volume, and synchrophaser is one of the substations spread across the hundreds of miles. And I have worked one of the project of in the North America is that National Frequency Monitoring Network, NF, MN. So this monitoring network, what it does, the frequency monitoring. So if you see the transmission line is connected and the sag became very low or the sag became very high, so the conductor comes the lower side of the to the ground. Mhm. So that is why large scale control action need to be designed which you can. Then mm, the media used for one communication no longer is there. So AMI, advanced metering infrastructure, is one of the very important topic distribution, and they execute the local network, and two-way communication is possible, and two predominant technologies like power line carrier and single transmission over utility distribution lines as designed. So if you see HN is home area network, and this is used in the inside the consumer's home. We use this one, and there is also we will see that what is the, and they are very efficient and they capture the very all kind of the data, and then they display this one. So if you see, there are a few low cost smart grid for rural electrification. So okay, sorry, something came. No, this is actually something recorded. Anyway, the proposed solar system, you have the DC bus and a solar MPPT boost converter is connected here, and then DC bus, and we have bidirectional battery charger and connected to this. So what we do, we have this is the cyber physical energy system. You can see that there are four sensors and the voltage point at the common mode common coupling. And two array of related nodes for the communication established. You can see that there are 1, 2, 3, 4 are the measuring instrument. Okay. And then we have 4 digits. They are interconnected. So how this is, if we see, if you see, this is a multi-input, multi-output system, and we can model this one in this way by using the control system model, and the control can be designed in this way. So if you see here, the model communication, NS, this is the number of the sensor, controller, and relay nodes are defined in this way. So if you see here, the this one is that the mode 1 battery and then discharge during this period, and also the mode 2 is a discharge, and then there is a generation. So if you see here, the there are load voltage, then DC bus voltage, then solar current, battery current waveform. You can see. Now you see when this load, then this load, you can see that the first solar current, battery current waveform, and you can see here that when there is a during night time there is no solar, so battery has to discharge that one. So this way, this is developed when there is a load voltage, and this during the transient from mode 3 to mode 2. Okay, if you see here, now this battery current is discharged. Okay, so this is our solar plant where we develop. You can see that we have developed online monitoring portal where all these, because the solar plant are connected in a remote rural village and nobody want to stay there. So we developed the online monitoring system. Here you can see here. This is the solar battery, then voltage, then load is given in this. So there are, you can see here, there are four battery solar. The solar or battery. So port 1, port 2 are different the switches. If you want to switch off port 1, port 2, anything, you can switch off by sitting in your home. And this way, this is the online monitoring portal, and this is the experimental setup where we have developed the DC-DC converters and all kind of consuming loads and data, all the thing for collection. And then we have a challenge one. The one is the advanced modeling methods is very important thing. One is structural properties. Means what kind of structural we need to develop for the particular geographical area, where if you can have contingency, renewable integration, interaction with the prosumers, and then scalability. One big challenge is to enable a real-time simulation. And there are few softwares where we can do that one also. And then model validation is one of the very important challenge. And even though you develop a model, whether it is working with the actual field or not, that is very important. For example, I'll give one example, real-time example, how the model is validate. So I remember we have got a 5 MVA transformer from Kello Square, Mysore. And when this transformer came here, we saw that the transformer has displaced the mechanical, due to mechanical vibration, the winding is displaced. And we develop a model for that one. We testing everything, and transformer bring and in a big vehicle it came here, and while bringing here, a complete transformer was vibrating, or so some of the winding shifted here and there. So how to validate then? The most important thing is that we need to understand the all the systematic design of this particular equipment or the particular network. That is why there are model aggregate. Okay, is one of the thing. The large size and external complex of any power system deriving this entire network extremely really challenging. So what we do? Approximate aggregate or reduced model, you can use it. For example, I'll show you in this picture only that how we developed a very nice large and medium and small scale the power system, and then market simulation, then load forecasting. Smart load and handling module uncertainty is a very important thing. So if you see this information and communication, you can see that there is a LAN and there is a HAN also, and this is the interaction between LAN and the all the wide area network. So what is the system requirement? First requirement is the grounding system. One, you set the limit that it can produce this much, and then our um, this DERs, distributed energy resources, they will also operate with some control and with power electronics components. They can keep some data. And also the network model, when we are doing for the microgrid design and planning, you will see that there is a bus voltage and circuit breaker data, transformer generation capable, the cable branches, all kind of thing is required. Then load flow analysis and short circuit, then data requirement. So this is a project given by the imprint project, what we got around 200, around 2.4 crore rupees. So the community microgrid development initiative and the community microgrid initiative, we have started the modeling the and simulating the microgrid, and then this microgrid we used the commercial software and also very costly. Hmm. And then we have developed the software model, like I'll show you. This is our software model. Design of a microgrid generation capacity. You put a capacity, for example, in this locality you required 150 kilowatt load. So you put here in this blank as 150 kilowatt, an average. Let's take peak load is 180 kilowatt. You put here. And renewable specification means there is ample amount of sun rays, wind, or temperature, or thermal, whatever things you want, you can specify that. For example, in Bihar, so you can put solar renewable specification, but wind is very rare actually. Very in the wind is not there in this particular place. So wind is removed, and then automated generation of initial discrete event model of the microgrid will be developed, and it will choose from the library we provided. For example, the switches, voltage control switches, generators, or the solar energy, whatever thing. It will collect from the library and put it. And we have done in using Open Modelica software, and then test bed. When you gave this one, then you have to optimize this. For example, so many components are given and many things are given, so you need to optimize few components you can reduce, so that cost will be lesser, will be reduced at the finally. And then if it is working fine, then develop the hardware prototype and test whether it is okay, and then use a deployment, or you use it, or you give this one. And this way, uh, in this way, this is the complete unit. It is this is the testing phase. So then we have on the Open Modelica. We have started. The step one is that one to develop the microgrid component first, and then microgrid model, and then component of microgrid, and then development and of the compiler and optimization phase, and then development of the real test bed. So these are the software where we developed all this, and you can see that the software is here. And then here you can see that software tools are used to generate or define the microgrid model. And then after this one, then we interface with S. So for example, design tool. Like one of this design is the line rectifier, battery, PV panel, and sample design microgrid. All those things are developed, AC-DC converter like this. And this is the so then we have developed a transmission line in IIT Patna. And there are also, I will show you how it is so beautiful. And solar PV enabled grid, interactive with microgrid for smart transmission line. If you see here, there are microgrid, and we want to transmit this proposed microgrid architecture. And each phase, this red one is the smart meters where you can control as a switch or as an. So total design or the up done by using this system, and proportional resonance converters are used. And then if you see, this is the transmission line. Is a short transmission line less than 80. Medium transmission line is around 80 to 40 kilometer. Long transmission line is greater than 240 kilometers. If we see here, this is the transmission line. Then this transmission, this is the model. And this is our developed transmission line. You can see that here we developed the transmission line. Now, in this transmission line, we have uh, three, um, three circuit breakers, smart circuit breaker. You can operate from the mobile as well. So, if you see here, this is the energy meter. And this is the best, one of the best imprint project which is selected for display. And for this project, we got also 40,000 rupees a student innovation award. So this is our and the complete hardware, and you can see here, and transmission system which we develop. So this was our. So we have developed a few microgrid project. One at IIT Patna, and another one in the Tennessee Tech. We developed this one, but there was no structural stability. It was not a grass-free land, and no optimum angle. Also, this one. So then another project we did in the Nashville, in near Tennessee, and this project is around 1 megawatt low. And also a small microgrid project in Hyderabad. Here we are designing this one. And then this is a 1 megawatt. Then this is a AC microgrid in association DC Power. We have developed for 1.2 kilowatt power capacity. This is one of the Toypur, is one village in the Baisali district, which we developed the complete unit for the 50 houses we supplied the load. And this is the solar micro Air, Air Force Station of Port Blair. And then this is the design. You can see that the complete design. And this is the all earthing pit of the design. And there another project we developed is the solar wind microgrid also. And here you can see that this is the wind-based microgrid. And this is your solar system, wind system, controller, and smart load. And one of this is given here. This is the isolated microgrid. And if you see here, this is our microgrid system which is developed in the Tennessee. And this is one of the microgrid you can see here. In IIT Patna, we develop both the horizontal axis and vertical axis wind turbines. So if you see, this is and this is one of also the high power current injection method of a high power drive system, and which is connected with the given network also. So this is our lab. Thank you very much. If you have any question or comment, we can discuss. Please.
Good morning, sir.
Ha ha ha. And
Sir, you showed one slide of cyber physical system modeling.
huh.
That you mentioned the software name Modelica.
No, we have not done using Modelica. That can be used. That is a low cost system for designing the which is we have. It is open source software, so that can be used for designing the microgrid, not in that cyber physical system we have. Cyber physical system we have used the same the PSIM software where we use a few components, and that is more over the practical things, not this one. Okay.
So can we use MATLAB simulating
And
CPU?
that also you can do. There is no problem. But there are some components which you cannot be implemented. For example, the temperature varying data, and you want to transmit those data, there will be delay, and all these things you cannot model directly. You need to be This can be modeled for an ideal system, not the exact system. Okay.
Okay. Okay, sir. Thank you.
If any participants wants to ask question, he or she can write in chat box. वो तो पहले
Ah. Okay, if you have any question, I am just giving my email address, and you can just I am putting chat box. If you required anything, also we have all kind of hardware. You want to do some hardware work, other things, you are most welcome to come to my lab. Okay? Thank you.
Thank you so much, sir, for your valuable insights to us on both on DC microgrids and its further applications. Thank you so much, sir, for your time. Thank you.
Thank you. Welcome.